Modern enterprise AI systems navigate knowledge bases spanning thousands of documents, but every prompt eventually hits a hard mathematical limit, the context window. It is a strictly fixed budget of tokens. Think of it like packing for a 2-week trip when you only have a carry-on bag. You cannot bring the entire closet. You must write a packing list for the essentials, tightly compress your clothes, and seal your toiletries in a separate bag to avoid a mess. That packing list is the equivalent of selecting only relevant data. Rather than dumping unstructured documents into a prompt, the system identifies the specific information required for the query. Rolling your clothes mirrors data compression. The system takes selected text and condenses it into denser tokens, fitting more information into the same space. Sealing liquids is isolation. This architectural step keeps specific data context separate to prevent the model from confusing different tasks or datasets. These strategies form the 4 pillars of context engineering: write, select, compress, and isolate. Managing the context window requires a precise pre-generation pipeline designed to maximize token efficiency before the model even begins its response. The first pillar, write, shifts the model from a passive consumer to an active context generator. We use the model to create highly structured, token-efficient notes for its own use. One primary method is the scratchpad. These are temporary workspaces where the model writes its reasoning step by step, providing a logical trail to follow. This chain of thought reasoning becomes part of the current context. The model reads its own reasoning to arrive at a more accurate final answer. We also use summarization as a context creation tool. Processing a 50,000 token legal contract in its raw form is inefficient and costly. We instruct the model to extract the core terms into a structured table, identifying parties, obligations, deadlines, and penalties. This process reduces the input from 50,000 raw tokens to roughly 2,000 highly usable tokens. Writing temporary context allows the model to compress its own inputs into actionable intelligence that fits easily within the token budget. The second pillar is select. Research shows that as irrelevant context increases, model performance often degrades because the model struggles to distinguish signal from noise. To maintain accuracy, the system must retrieve information from the source aggressively, then filter it down until only the essential data remains. The first layer of this filter is vector similarity search. It captures concepts that are semantically related to the user's query and discards the rest of the database. To catch precise terminology that semantic search might overlook, we apply a second layer, such as BM25 or keyword matching. Finally, metadata filtering enforces hard constraints, such as specific document dates or verified source origins. While high-volume data enters the top of this pipeline, the multi-layered filtering ensures a highly refined output that fits safely within the context window. This selective process prevents context bloat by ensuring the model only processes information directly relevant to the current task. Pillar 3 is compress. This phase focuses entirely on increasing the density of information per token. MapReduce summarization splits a long document into chunks. Each chunk is summarized independently in parallel, and then those summaries are merged into a single final document. MapReduce is efficient for large-scale processing, but because each chunk is summarized in isolation, it can lose connections that span across the different sections. Refined summarization is the sequential alternative. The system summarizes chunk 1, then uses that summary plus chunk 2 to create an updated version, repeating this through the entire document. This method is slower to compute, but it maintains a continuous line of reasoning from start to finish. For complex enterprise systems, we use hierarchical summarization. This maintains summaries at the document and section levels, only zooming in to detailed paragraph text when the specific query requires that level of granularity. We can also apply token-level compression. Tools like LLM Lingua 2 use models to identify and remove filler words and redundant phrases, achieving up to 10x compression while keeping the semantic core intact. These techniques are far more effective than basic sliding windows, which simply delete the oldest parts of a conversation to make room for new tokens. Hierarchical windowing solves this by keeping recent messages in full detail while progressively summarizing older history into bullet points or single paragraphs. Advanced compression ensures the system maintains document awareness without exceeding the token budget. The fourth pillar is isolate. This involves creating strict, scoped views for individual AI agents within a larger architecture. Consider a multi-agent system with 3 specialized nodes: billing, tech support, and shipping. If a user asks about a late package, feeding the billing agent's credit report data to the shipping agent creates a security risk and an unnecessary expenditure of tokens. Accuracy improves when we remove these distractors. Isolation ensures the model isn't confused by information that seems relevant but isn't. We implement this through scoped context builders, functions that assemble a unique context window for each agent based on its specific role and security permissions. Isolation protects system security and keeps each agent focused on its specific task. This trace shows how the entire pipeline functions in a split second before the first response token is generated. It begins by selecting the relevant document chunks from the knowledge base. The system then compresses those chunks to maximize the information density. Next, the system is writing a structured extraction of that data into a reasoning scratchpad. Finally, this context is isolated and routed only to the specific agent required to answer the query. Only after these steps are complete does the agent generate the final output. The first 2 pillars are: write structured formats to offload intelligence, and select data aggressively while filtering ruthlessly. The final pillars are: compress to maximize data density, and isolate to enforce focus. Mastering the 4 pillars of context engineering turns the fixed token budget into a precisely engineered architectural advantage.